we need the notion of path integrals. How do you integrate a function that is defined on a metric space along a path? Let's say a rectifiable path, or even Lipschitz path for simplicity. So given a reasonably nice function on a metric space and a Lipschitz curve, what is, or what should be, the value of integrating this function along this curve? Let's say ds is the symbolic arc length parameter to do integration against. So the easier way of doing this will be that if rho is Borel measurable, and gamma is parameterized by arc length, which we know exists whenever gamma is rectifiable, in particular whenever gamma is Lipschitz. By the way, I've never written down this, but it's immediate from definition that Lipschitz curves are, in particular, rectifiable. They are a subset of that collection. So if you start with a Lipschitz curve or a rectifiable curve, you can reparameterize it to be arc length. Then rho composed with gamma, which will be a function from this domain of the reparameterization, which is 0 to the length of gamma, into, well, rho takes into x, and then gamma takes into x, and then rho brings it back to r, so this is into r. Now we're dealing with a very concrete case of a real valued function defined on a compact interval. So then this function is L1 measurable, Lebesgue measurable. This is where you need the assumption of Borelness. If rho is itself just measurable, you don't get this. Also, before you have a measure introduced on the metric space, it's not even clear what is rho is just measurable against what measure. But Borelness, remember, only requires the metric properties. So if you have a Borel function and an arc length parameterized curve, then this composition will be L1 measurable. That's the proper way of doing things carefully. And therefore, this integral from 0 to the length gamma, so integrating over that interval, this L1 measurable function t dt is well defined. It could be infinity, but it is well defined. Also, we can allow this rho to be into not just r. We will need it for non-negative functions, but they could at some points be infinity. So therefore, this can also be into 0 and infinity included. And this we will take to be the definition of integrating rho over gamma. So we take this to be the meaning of integrating rho along gamma ds. Here we haven't really made any free choices, so we don't need to prove anything regarding that this is independent of choices, because the arc length parameterization is unique, and then we didn't make any other choices. This L gamma is forced from arc length parameterization, and everything follows. So this is the shortest way to define the path integrals. of non-negative Borel functions on curves. Although this is simple and elegant, the problem is in reality we can't usually easily arc length parameterize curves. I gave you this exercise of the Cantor-Vitale function and look at its graph as a curve and try to compute its arc length parameterization. It's not that explicit, that simple. So we need some probably other characterization. If gamma from A to B into X is Lipschitz, then this quantity, which we can say, well, we want to define speed. The way we do it in Euclidean case is we define gamma prime, it's a vector if this is Rn, and then we take the norm to integrate. But because we don't have that notion of a vector in a general metric space, we only can define the speed really. And this will be the limit of, well, t, you try to mimic the Euclidean case, so you do a perturbation in the t variable, so you go from gamma t plus s to gamma t to gamma t plus s. You cannot subtract them. These are just, the metric space could be just a finite number of points. But all you can do is you look at the distance of these two values, and then you divide it by this change in the parameter s, and you let s go to 0. So then this quantity is well defined almost everywhere. To be precise, for Lebesgue, almost every t in this range AB. And two things happen. They're both equally useful. Number one is that the length of gamma, which is defined through this supremum over partitions, is equal to this speed of the curve from end to end. And number two, which was the main reason for this, is that we can integrate already with this parameterization, that for Borel rho function from x into 0 plus infinity, the integral rho ds that we defined above, which required first arc length reparameterizing and whatnot, is equal to integrating over original range of parameterization with the original gamma without really perturbing it. So this will be rho evaluated at gamma t, and then you multiply into the speed evaluated at t dt. So this is the more significant part of this theorem. Of course, if you apply this result with rho equal constant function, you kind of recovered the previous one, I want to say, but then I don't know where you exactly get the length. Okay, so if you have Lipschitz curves, then without arc length reparameterization, you can obtain this. This is very useful in case where you only need like inequalities. For example, this quantity is always bounded by Lipschitz constant because here the numerator is bounded by Lipschitz constant times s. So you can immediately get some inequalities like rho. And if you know rho is bounded, for example, yeah, so this will be Lipschitz constant, the L infinity norm of rho and things like that, times b minus a, and you get very useful inequalities from this, which is not immediate from the other definition on the left using arc length reparameterization. Okay, a more difficult, substantially deeper alternative characterization of this integral is, well, let me draw you a picture. So here's your metric space X, maybe disconnected with some other values, and then there is the curve gamma in there, which can self-intersect. And also remember, a curve can go back onto itself, traverse some segment twice, and then leave. And then you have the function rho from x into 0 plus infinity. Well, with curves, we can think of Hausdorff 1 measure h1. And this theorem recovers the path integral via integration against this Hausdorff measure. So let gamma from AB into x be Lipschitz, and rho from x into 0 infinity Borel. Then integrating rho on gamma according to previous definition will be equal to integrating over the image of gamma. So this is like making it more intrinsic, so as the subset. So how can we integrate this function over the subset, all happening inside the metric space, and recover that quantity which is kind of extrinsic, coming from a parameterization of the curve? Can we truly integrate looking at this set? The answer is yes, and that will be, well, you integrate over x, but technically this will be only over the image of gamma, the set of gamma t. But there will be no harm in putting this x, because in irrelevant parts the integrand will be 0. So you want to say I want to integrate rho of x dh1 of x. So x is a point here in the space, or if it's here we will get 0. So really the integration will be happening along the curve. And then remember that this part of the path is traveled twice, so only looking at the image of the set will not be enough, because what if you have a loop and then you travel along it twice? So the integral over that should be twice integrating over the circle. How do you capture this? What about points where you cover 3 times? What about, like in this picture, only some segment of the set you cover twice? And those all are captured by this one. So this will be the number of times, the cardinality of the set T where gamma T hits X. So this is an integer valued, possibly plus infinity. Some points can be met actually infinitely many times, but not many points will be, because this path, remember, is rectifiable. It accumulates only finite length at the end of the day. So this is the right index, the right quantity, which corrects for all these multiple coverings. And remember, if x is not in the path of the curve, you don't hit it, this will be 0. So technically this integration reduces to just the image of the path. And you see here that there is no mention of this speed of the curve. Basically nothing comes from the curve here. All of it is taken care of with this dh1 measure. This takes a simpler form if this gamma is injective, no point gets covered twice. Then integral gamma rho ds is simply integrating over, well, let's say this set gamma t where t belongs to AB. Simply rho x dh1. This emphasizes the fact that integration over path is kind of intrinsic. It really happens on the space x, and it's independent of different parameterization of the same curve. This could be also deduced from the original definition. If you have two curves, gamma and gamma prime, or tilde, if these are the same curves up to reparameterization, then their arc length parameterization will be exactly the same thing. So integral over gamma will be integral over gamma tilde. This shows that there is some intrinsic features to this integration. If you, in a very artificial way, change your path or curve or parameterization of your curve, here we mean parameterization. If you change the parameterization in an artificial way, this quantity does not really change. So in that sense, it's really intrinsic. So all of this regarding path integrals. Again, if you want more details, go to my full playlist on curves in metric spaces and Euclidean spaces, where I do other examples and compare to the Euclidean case. This coincides all of this with what you learn in calculus, that if you have, again, an injective path, or injective except for the endpoints, where, because you want to include the loops for Stokes theorems and Green's theorems and stuff like that, where you define integral along a path, there this becomes the definition. What we showed above, that this is f of gamma t, and then you have gamma prime of t dt. You call this like the arc length factor, or ds, and from A to B. You take it as definition in calculus. What you don't do is showing that this is really independent of whatever parameterization you take. So you do a lot of these integrals in calculus where you want to go around the circle once and say you want to integrate a vector field or a function along this circle loop. And then you say, okay, let's take this parameterization cosine t sine t, and then you go ahead and plug that value into here and take derivative here, take absolute value, and do everything. But most undergrads never question whether, well, what if someone else takes a very different parameterization? Will they get a different value for this integral? The answer is no, and should be no. And the reasoning is the lemmas and theorems above that I mentioned. So as a recap, just to make sure, because we will use this a lot, what we did was we define the notion of integrating a Borel function on a rectifiable curve. And the definition is via first arc length parameterization and doing the obvious thing. But then we saw that if you have a Lipschitz curve, you can mimic the Euclidean case by mimicking the speed of a curve. So the difference is that in Euclidean case, gamma prime really is a vector, and then you take absolute values so that you obtain a speed, take away the direction, the velocity from it. But in the metric setting, you only have a definition, a suitable definition of the speed and not the vector. For most purposes, just sticking to that original definition will be enough, but I wanted to show you why kind of the definition is natural and what it connects to and relates to. Now we are ready in next video to talk about upper gradients, the building block of the Newtonian Sobolev spaces. Until then, have a good one.